Today we're going to find the length of an arc. And you might ask yourself, well, what does that mean? Well, let's say we have y equals f of x defined as you see here on your paper. And basically the length of an arc, if we had one of those wheels that you roll along the ground to measure distance, if we were to be able to roll that wheel along the path and measure the length of the path from the left end point all the way to the right end point, we'd have the length of our arc. We could also think of this as if we could straighten out that arc and stretch it out and just measure with a ruler or whatever the length of that line from the left end point to the right end point. So that's what it means to find the length of an arc. Okay, so but we can't do that, and we have to deal with well, let's use some calculus to figure this out. Okay, what you see here is you see 9 points, or 10 points actually, P0 to P9, all along the path. And what we want to do is we want to break this curve down into many line segments. Okay, so you can see that the P2 to P3, that's one line segment. That's not even on the curve. P1 to P2 is another line segment. But you don't have to worry about all that. You have to go, if you want to really understand what's going on here, all you have to do is connect the concepts to what you used to do and what you're going to be doing now. If you remember, when we found the area under a curve, all we did was we found the area of one rectangle and we integrated that from A to B. That we found the area of the curve. Area between curves was in section 7.2, and if we wanted to find the area between curves, all we had to do was find the area of one rectangle again, which would be f of x minus g of x times dx, and then we'd integrate from A to B. Okay, and then we got into volume, section 7.3. If we found the volume of one cross section, in this case it would be a disk, pi r squared dx, and r was f of x. So pi f of x squared dx gives us the volume of one disk, and if we integrate from A to B, we get the total volume of that region, total volume of that solid. Okay, so fast forward to 7.4, and we've got the length of an arc. Okay, so if we want to know the total length of the arc, we're going to find the length of one line segment. And here, as I said, we're going to be deriving, or maybe I didn't say that, but we're going to be deriving these formulas in class. And so you just have to trust me now that ds represents the length of one line segment. I'm just going to call it one segment. Okay, so ds is the length of one line segment. And if we can find the length of one line segment, we can integrate from A to B or from C to D, depending. Okay, so if our curve is defined as y as a function of x, then we're going to integrate from A to B, the leftmost x to the rightmost x, just like we've done in our areas and in our volumes. Okay, if by chance our curve is defined as x as a function of y, then we're going to integrate from the lowest y, c, to the highest y, d, and we're going to get the total length of the curve. Okay, I'll let you read the stuff on the bottom later, but let's go ahead and get into our first example. Okay, so example 1, the length of this curve here, y equals ln of secant of x on the interval from 0 to pi over 4. We're going to assume, we make some assumptions here. From examples 1 through 4 today, we're going to be just assuming that these curves are defined and continuous over the entire intervals that are given. Okay, so let's remind ourselves, here we're integrating from y as a function of x, and we have x there. So check those first. And when we integrate, we're going to be finding the length of the arc, and that's going to be from 0 to pi over 4. And let's remember our formula, 1 plus, if you rewrite the formula every time, then it'll be easier to remember. So we're going to have dy dx squared dx. Okay, that's a bad d right there. So that's our formula. So let's find our dy dx. So as soon as you look at the formula, you realize, well, what do I have to do? Oh, I just have to find dy dx. Okay, so our dy dx is, all right, so now we have a derivative, so it's good. We get to practice our derivatives. The derivative of ln of anything is 1 over the anything times the derivative of that anything. That's secant x, tangent x. So the derivative of the secant is secant tangent. Well, as we can see, we can cancel the secants and we get tangent of x. And now, I'm a pretty lazy person by nature, and I don't like to rewrite a bunch of stuff. So I'm just going to put a squared outside each of these guys. And that's what I'm looking for. I'm looking for dy dx squared. And if I don't do that now, I might forget to do it later, which is a big reason why students miss these problems, why anyone misses these problems. And so we can go right to our length. Okay, 0 to pi over 4, integral from 0 to pi over 4, radical 1 plus, and we have tangent of x, so dy dx squared is tangent of x squared, or tangent squared of x. Okay, now I'm really testing your memory here. See if you can remember what 1 plus the tangent squared is. Yep, that's the secant squared of x. Good job getting that right away. And then now the square root of the secant squared would be the absolute value of the secant of x. So I know you knew that as well. But do we need the absolute value bars from 0 to pi over 4? No, the secant is positive. Secant is 1 at 0, but it's positive all the way to pi over 4. So we really don't need that. Not really, we don't. We don't need the absolute value bars, but it's important to, it's important to make sure you recognize that in general, the square root of something squared is the absolute value of that something. Okay, so where are we at here? What's the integral of the secant of x? Well, that's a bit tricky. Okay, so I'm not going to make you do that. I'm just going to give you the formula, and we're going to go all the way back over here. And the antiderivative of the secant of x happens to be the ln of the absolute value of the secant of x plus the tangent of x. Okay, and we're going to evaluate this antiderivative from 0 to pi over 4. Okay, and now we just get the ln of the absolute value. Secant of pi over 4, okay, 1 over cosine. Cosine is radical 2 over 2, so this would be 2 over radical 2. Tangent of pi over 4, we know that that's 1, minus the ln of the absolute value of secant of 0. Well, we just said that. Secant of 0 is 1. Tangent of 0, that's 0. Okay, so this whole thing here, we get ln of 1, and we know ln of 1 is 0, so that's just minus 0. So we have our answer. I don't really care if you rationalize that denominator, nor do I care if you leave those absolute value bars in there. And now that we see what we have inside the absolute value bars, we know that that's positive, so we know we don't need the absolute value bars. So what I would do if I were you is I would, like I said, keep the calculator handy, and let's go ahead and take a look and make sure we got the right answer. Okay, so we're going to type in, we don't need that stuff there. In fact, we don't even need that. We can just type in math 9, and we're going to just go right to 0 to pi over 4, 0 to pi over 4, and that would be secant of x. And so secant is 1 over cosine, 1 divided by cosine x, okay, and that's dx, and we get a number that we see there. Well, we don't see that on our paper, so now we have to figure out what is the ln of 2 over radical 2, so we can go 2 divided by square root of 2, and then what do we have, plus 1? Plus 1. And we hope we get the same answer, which we did, so nice job.